Okay, Chemistry 111. I wanted to talk to you a little bit about Chapter 11. And I do have some slides that cover the content of Chapter 11. But Chapter 11 deals with intermolecular forces. And I just want to introduce the subject to you first a little bit. So intermolecular forces, we sometimes abbreviate these as IMFs, intermolecular forces. Let's say I have a molecule of water. Everybody knows how to draw a molecule of water. We draw a Lewis structure like this. Sometimes we draw it in this way to show that this bond angle is a little less than 109.5 degrees, whatever. Again, everybody knows how to draw the Lewis structure of water. But there are forces that hold a water molecule together, aren't there, right? We see that we have a sigma bond here, right? A sharing of 2 electrons between this oxygen and this hydrogen. And we also have a sigma bond here between this hydrogen and the same oxygen, a sharing of 2 electrons. So these are sigma bonds, right? These are actually covalent bonds. So they're sigma bonds, they're covalent, okay? It's the sharing of electrons. And we call these intramolecular forces. Those are the forces that hold the molecule, the actual molecule itself together. So intramolecular forces are like saying the bonds, right? You've probably heard the words international and intranational. If we're talking about international travel, that would mean travel between 2 countries. However, intranational travel would mean inside the same country. So if you were traveling between states, let's say, you could call that intranational travel. And so intramolecular forces are the forces inside the molecule that actually hold the molecule together. Well, I still haven't covered the concept of intermolecular forces yet, have I? Okay, well, let's say we have 2 water molecules. Let's say we have 1 water molecule here, okay, and we have another water molecule like this. Well, what do we know about the polarity of the bonds in a water molecule? We know that there's a dipole going this way and a dipole going that way. And we talked about molecular dipoles in the last lecture. So we know that water is a polar molecule that has most of the electron density near the oxygen because it's more electronegative than the 2 hydrogens, which are electron deficient. So if I have a second water molecule, I could draw the same thing like this. I could say the delta plus is near the hydrogens and the delta minus on the oxygen like that. So the idea behind intermolecular forces is this. If I have these 2 water molecules, what are the forces that hold water molecules together in a sample, right? If you have a glass of water, okay, you've got some water inside this glass. What are the forces that hold the water molecules inside the glass that prevent them from just spontaneously vaporizing from the liquid phase to the gaseous phase? Now we know that some of the water molecules at room temperature will have enough kinetic energy to escape from the liquid to the gaseous phase, but most of them won't. And so the question is, what are the forces that hold the water molecules together inside the liquid? And the answer is they're intermolecular forces. So what's going to happen if I have all these delta pluses and these delta minuses? What's going to happen is a delta minus, say from an oxygen, is going to come close to the delta plus from a hydrogen on an adjacent water molecule, and there's going to be an attraction between those 2. Let's say I have another water molecule, for example. I'll just copy this one and paste it. Okay, now I've got another water molecule. What would prevent it from doing something like this? Right now I have an interaction between this delta plus and this delta minus, and this delta plus and this delta minus, right? Opposites attract. Opposites attract. Okay, so just by virtue of the fact that water has a dipole in the molecule, we have the delta pluses and the delta minuses attracting one another. Now, these are not covalent bonds, are they? These are just an electrostatic attraction between a partial positive charge and a partial negative charge. It's not an ionic bond either. These are intermolecular forces. These are the forces between the water molecules that hold them together in a sample. And we'll talk about those even more. Now, if you read chapter 11 already, you'd know that the forces that I'm representing here are called hydrogen bonding. We'll talk about those in more detail a little bit later. Okay, but before we move on, I want to share something with you that's even a little bit more complicated. What if you had a molecule of ethane? Now, if you don't know what ethane is, I'll draw it for you here. Ethane is a hydrocarbon, just like octane is. If you've gone to a gas pump, you know what octane is. Well, in the molecule ethane, okay, so this is an ethane molecule that I've drawn here. This is a completely nonpolar molecule. There are no polar bonds in the ethane molecule. Now, if I had a second molecule of ethane, okay, so I'll just copy this and I'll paste it over here. What in the heck would cause these two molecules to be attracted to each other, right? There's no dipole in this molecule and there's no dipole in this molecule. We just said that opposites attract, right? Based off of Coulomb's law, we have an attraction between partial positive and partial negative charges. Well, here's where it gets interesting. Let's just say, instead of thinking of all these sigma bonds as the sharing of two electrons, what we do is we think of all of the bonds sort of sharing the electrons, or we think about the molecule being surrounded by a cloud of electrons. And that's what I'm representing by this red sphere here. This is kind of like an electron cloud. Okay, so all the electrons moving around in those bonds are free to move around the molecule. Well, as one of my friends always says, you know, electrons are like hyperactive children. If you give them space to move, they're going to move. So if the electrons that are in those bonds, if they can now move around anywhere inside that electron cloud, they're going to do it. Right? So now what we've got is a bunch of little electrons, right? We'll just draw some like this, okay? We've got a whole bunch of electrons just evenly dispersed throughout that cloud. Now again, electrons like to move, don't they? And they move really quickly. Okay, they move very quickly. So isn't there a small probability that at one moment most of the electrons might, and I'm not saying it's going to happen all the time, but let's just say that all of a sudden all of the electrons end up on one side of the molecule. I'll put them all over here. And this is just based on probability, right? If they're all moving really fast, then there is a probability that all of the electrons might end up on one side of the molecule. What effect is that going to have on the electron cloud? The effect is this. On the right side of the electron, or sorry, the right side of the molecule or the electron cloud that I have drawn, since you've got most of the electrons over here, you're going to have a big old delta minus here. And then you got no electrons over here, so that side is going to be delta plus. Right now, what do we know? Opposites attract, like charges repel. So if the adjacent molecule of ethane has a whole bunch of electrons, right, dispersed all perfectly evenly, they're all having a nice day, you know, having a picnic or whatever, all of a sudden, when all of these electrons bunch up on one side of the molecule that's adjacent to it, what's it going to do? It's going to repel all these ones, which is going to push them over here, right? It's going to move them over here like this, and you're going to end up with the same effect that you saw with the other ethane molecule. Now you've got a big old delta plus over here and a delta minus over here, and now you've got an attraction between these dipoles, okay? Every molecule can experience this type of intermolecular force that I've represented here. This is what's called a London force, or is sometimes called a dispersion force. Okay, so this would be called a dispersion force. Now, a dispersion force is weak. Why is it weak? Because it is fleeting. Okay, it is temporary. That's another way of saying fleeting, temporary, right? It is fast. Right, what I'm saying, again, listen to me very carefully, is if just spontaneously all of these electrons move to one side of the molecule, they're going to repel all these electrons, and then you're going to get a delta minus and a delta plus, and there's going to be an attraction. But I just told you guys that these electrons are moving really fast, so then all of a sudden they're going to go, you know, and evenly spread out again. So this is a very quick thing. But this is why nonpolar molecules nonpolar molecules rather, experience some kind of intermolecular attraction. Give me a thumbs up if these two concepts of a polar molecule like water having a permanent intermolecular force, right, because these dipoles are permanent, or a nonpolar molecule having an attraction that we would call a London force, okay, or dispersion force, just based off of the probability that the electrons are moving around the molecule. Thanks, Christina. All right, great, excellent. Well, if you understand what I just said right there, then you won't have that much of a stretch understanding what is going on in chapter 11. So let me just scroll down here to chapter 11, and we'll talk about intermolecular forces and a little bit of information about liquids and solids, right? Everybody here knows about phases already, so most of this should be a review of phase, right? You talk about the phases of matter, solid, liquid, and gas. Phases are homogeneous, right? It's a homogeneous part of a system that's in contact with other parts of a system that is not in the same phase because they're separated by a well-defined boundary, right? You put ice in a drink, you usually don't look at it and say, no, where's the ice and where's the what? No, you can see there's a clearly defined boundary between ice and water on in a cold drink, let's say, on a hot day. Well, what are the characteristics of gases, liquids, and solids? Again, this is something that we would have looked at earlier on in this class, and I'm sure you've seen this maybe in a high school chemistry class. Let's go over it quickly. In terms of the volume of a gas, a gas will take up the shape of any container you put it in. Even if you put a gas in a room, the particles are going to spread out and they're going to fill up this space. So in terms of the distance between particles in a gas, the distance is very great. So gases are actually mostly empty space, and that is why they're so darn compressible, right? We can compress a gas. They have low densities, and the particles inside a gas are going to be moving very quickly. Well, when we move to a liquid, right? Liquids have defined volumes, but they will always take on the shape of whatever container you put them in. So defined volume, however, an undefined shape will always take on the shape of its container. Can you compress a liquid? Yes, slightly, but the fact that liquids are so incompressible, or their compressibility is so low, this is one of the reasons why we have brake fluid, right, and brake lines. But in terms of the motion of the molecules, we can pour a liquid, can't we? And when we pour a liquid, the molecules slide past one another. Well, let's move on to the solid. Definite volume and shape. Everybody, I'm sure, knows that. The density of a solid is high, just like the density of a liquid, where the particles are all packed close to one another. Virtually incompressible because the particles are so close to one another. But unlike the liquid, where the particles could slide freely past one another, in a solid, all of the particles are going to be in fixed position. So that's a little information about phases, the solid, liquid, and gas. Well, now we're getting into the nitty-gritty of intermolecular forces. And I just introduced these two concepts to you. An intermolecular force is the force of attraction between two molecules. I'll give you another example. Let's say I have two molecules of carbon dioxide. Carbon dioxide is a nonpolar molecule, but there's got to be some force of attraction between two molecules of carbon dioxide in the gaseous phase, right? And that would have to be London forces. We'll talk more about that later. And then we have, of course, intramolecular forces. Those are nothing more than bonds, right? That's the covalent bonds, or whatever force that holds atoms together in a molecule. So if you think about the strength, the relative strength of intermolecular forces versus intramolecular forces, an intermolecular force is going to be the weaker of the two, right? Much weaker, okay? If you want to vaporize 1 mole of water, what's vaporization? Vaporization is going from the liquid to the gaseous phase. So if you just want to take 1 mole of water, so what's that, around 18 grams of water, and you want to boil it, well, what do you have to break? What forces do you have to overcome? You have to overcome the intermolecular forces between the water molecules in the liquid phase. Okay, it takes about 47 kilojoules to vaporize that 1 mole. However, if you have 1 mole of water and you want to break all of the oxygen hydrogen bonds, it takes a lot more energy, doesn't it? More than 20 times the amount of energy. Why? Because intramolecular forces are much stronger, right? It says here in the bottom left that generally intermolecular forces are going to be much weaker than intramolecular forces. So when you see things like the enthalpy, or the heat of vaporization, which is the conversion of a liquid to a gas, or fusion, which is a solid to a liquid, or sublimation, which is a solid to a gas, right? We're going from a more ordered state to a less ordered state. And so what are we doing? We're overcoming intermolecular forces. And so when you see these things like heat of vaporization, fusion, or heat of sublimation, they're kind of just a measure of the strength of intermolecular forces, right? The more energy it takes to melt a substance, It tells you if substance A has a higher melting point, generally speaking, it's going to have stronger intermolecular forces than substance B, let's say. Okay, well, let's get into some more nitty gritty about these intermolecular forces. I already shared this idea with you on my blank sheet just with respect to water molecules, but let's think about something even simpler. Okay, let's just say you have some generic hot dog shaped molecule. Okay, the old hot dog here. Yeah, and let's say it does have a permanent dipole, right? It's got a permanent dipole in this direction. Well, when you have a bunch of those molecules probably in the liquid or solid phase, what are they going to do? They're going to orient themselves so that all of the did I put two partial positives? That's not right. So that the partial negatives and the partial positives are going to be lined up, right? Because we have a force of attraction, right? All of these forces of attraction. And so the forces of attraction are minimized when our polar molecules align. An example of another polar molecule, just write one off the top of my head here, would be something like formaldehyde. This is the structure of formaldehyde, right? There's a dipole here between the carbon and the oxygen. That means the oxygen is going to be partially anionic, and the carbon will be partially cationic. So if I have another molecule of formaldehyde, what's it going to do? Well, if I have that delta plus at the carbon and the delta minus at the oxygen, that means there's going to be a force of attraction between the delta plus on one carbon and the delta minus on another carbon. So this is what we call a dipole-dipole force, because both of the molecules have a dipole, right? All of the molecules here have a dipole, and that, again, is why we call it dipole-dipole force. What if I have a permanent dipole in a molecule? Here's my hot dog molecule again, and I have an ion present in solution, right? What if we have a polar molecule in a solution, let's say, and then we have some ions in that solution, cations and anions? Well, the cation is going to tend to line up with what? The partial negative charge in the polar molecule, whereas an anion would tend to line up or be attracted to the partial positive charge in the polar molecule. So this is what we call an ion dipole force, and we see ion dipole forces when we dissolve a salt in water, and I have a figure that shows that coming up in a few seconds. So an ion dipole force, and you should know what a dipole-dipole force is and what an ion dipole force is, right? Everybody knows what a cation and an anion is, and you now know what a polar molecule is. So again, we just get that electrostatic attraction, positive and negative, right? Negative and positive. All right, let's move on from there. A dispersion force, which I explained to you, is probably the most difficult of all the intermolecular forces to explain. Now, what I did is I said, let's say you have a nonpolar molecule like this, right? You got this nonpolar molecule, but then all of a sudden, all of the electron density ends up on one side of the molecule, so the other side is just rendered partially positive. Well, that's one way that there can be an intermolecular force between two nonpolar molecules. But what if I have something that does have a charge, like a cation, and a nonpolar molecule? Well, if the cation has a positive charge, what's it going to do? It's going to pull any electrons in that nonpolar molecule towards it. So it induces or causes a dipole to be formed in that nonpolar molecule. So that's a cation and an induced dipole. Again, this molecule originally was a nonpolar molecule. However, once it saw that cation, all of the electrons in that nonpolar molecule said, that looks pretty good. I think I'm going to go over to the left side of the molecule so that I can be attracted to that lovely cation over there. Similarly, let me delete some of this spinach here. What if we had a polar molecule? Right, a polar molecule's got a permanent dipole. So let's say this molecule's got this permanent dipole going this way. We've got our delta plus over here. Again, what's my nonpolar molecule? What are those electrons going to do? They're going to say, oh, baby, look at that positive charge over there. I'm going to get attracted to that positive charge. And therefore, the polar molecule induces or causes that dipole to occur in the nonpolar molecule. Right? I feel like I'm explaining myself a bunch of times, but I want to make sure you understand that in this red molecule, normally that's a molecule where most of the time, all of the electrons are just perfectly spread out evenly. right? And there's two possibilities for a dipole to happen. You can either induce a dipole, or they can all the electrons could randomly move to one side, but that's a very brief process. That's a fleeting process. All right, well, let's take a look at dispersion forces in even more detail, because dispersion forces are the kind of forces we see in nonpolar molecules. Right? If a molecule doesn't have a dipole, what's the only possible intermolecular force it could have? It doesn't have a dipole-dipole force. And it's not going to have what's called hydrogen bonding, which we'll look at in a second, because hydrogen bonding is just basically a type of dipole. And so dispersion forces are the forces felt in nonpolar, most of the time in nonpolar molecules. Technically, dispersion forces can be experienced by any molecule, but this slide is getting at it with respect to, or trying to explain it in terms of nonpolar molecules. Okay, so if we take all of the molecules that are over here, we have methane, tetrafluoromethane, tetrachloromethane, tetrabromomethane, and tetraiodomethane, all of these molecules here. Each one of these molecules has the same molecular geometry. Watch very carefully, okay? They all have this molecular geometry where they have something here, something here, something in the back, and something here. So all 5 of these molecules are perfect tetrahedra. Well, if they're all, tetrahedral, they're nonpolar, right? Because it doesn't matter whether the dipoles are going this way or if they're going this way, they're all going to cancel because they're all spread out perfectly evenly with that 109.5 degree bond angle. Why in the heck would there be a variation in melting point? Why would it increase going from methane all the way up to CI4? Right? There's got to be a good reason for that. And the reason is this. It's based off of what's called the polarizability. Right? What happens when we go from a hydrogen atom to a fluorine to a chlorine to a bromine to an iodine? Is that the atoms get bigger and bigger and bigger and bigger, right? We increase the highest principal quantum number. If you look at hydrogen, it's in group 1. If you look at fluorine, it's in group 2. Chlorine is in group 3. Bromine's in group, sorry, did I say group when I meant period? Bromine's in period 4, and iodine's in period 5. So we could write that down here, period 5, and hydrogen is in period 1. So let me get into that concept of polarizability. It's based on this. The bigger the electron cloud, the more easily it is polarized. And polarizability is nothing more than the ease with which the electron distribution in the atom or molecule can be distorted, right? Can be, swayed to one side or another. Okay? It's kind of like this. If you have the methane molecule, and this is not the best, this is just kind of artist rendition, right? If you have a methane molecule, you've got the carbon surrounded by 4 hydrogens, and those hydrogens are small atoms, right? The electrons that are shared between the carbon and hydrogen are going to be a lot closer to the carbon nucleus, whereas if I have CI4, it's a much bigger molecule. And so it's a lot easier for the electrons in the periphery to sway from one side to another, and that's what polarizability is. Now, if you just want to memorize that polarizability is going to increase, if you've got more electrons, okay, the electron cloud can diffuse more, even if you just remember more electrons. That means you're going to have stronger dispersion forces, right? Dispersion forces usually increase with molar mass. Why? Because as molar mass increases, we have more electrons. Okay, so that's why CI4 is going to have a higher melting point than methane, CH4. All right, give me a thumbs up if you follow me on the concept of polarizability, which is basically the ability of an electron cloud to distort itself, right? To generate that induced dipole. The more distortable it is, for lack of a better word, the stronger that dipole can be. Okay, well, here's something that's really interesting. You've heard me mention hydrogen bond. If you've studied biology, I'm sure you've heard of hydrogen bond, and I've probably even brought it up unknowingly or not on purpose throughout the course of the semester. Well, by now, by 5:30 this evening, you know what a dipole force is, right? Between 2 permanent dipoles in a molecule. Well, a hydrogen bonded to either a fluorine, oxygen, or a nitrogen can actually form a special kind of dipole. Okay, so let me repeat that. And I know they're written right here, but I want to write them up here in the top right corner. If you have a hydrogen bound to an oxygen, if you have a molecule that's got a hydrogen bound to a nitrogen or a hydrogen bound to a fluorine, you are going to have, or you can have, what's called hydrogen bonding. Now, let me get some semantics out of the way here. Number one, hydrogen bonding is not a bond, okay? It's not a covalent bond. It's not an ionic bond. And if you're like, oh, come on. Well, I didn't invent the term, okay? The reason they call it hydrogen bonding, quote unquote, is because hydrogen bonds are usually so much stronger than dipole forces or London forces that they just call them hydrogen bonds. Okay, again, don't get angry at the messenger. It's just how they named it. Okay, so it says here hydrogen bond, special dipole between a hydrogen atom in a bond between nitrogen, hydrogen, oxygen, hydrogen, or fluorine and hydrogen. Why would these elements be so special? It's based off of two things, really. It's based off of their size and their electronegativity, right? Because all of these are small atoms, and you have that strong dipole going this way. So when you represent a hydrogen bond, the way that you represent it is as is shown here. You always show the hydrogen bond between a lone pair on the more electronegative atom, and then you draw dots going over to the less electronegative element. Now, I like to include this. By the more electronegative element, which here is oxygen, I like to put delta minus, and I like to put delta plus here. Okay? Same thing. Here's ammonia in water, right? Ammonia dissolves in water to make ammonium hydroxide. Well, on my hydrogen, I know there's a delta plus, and on my nitrogen, it's much more electronegative than hydrogen. I know there's a delta minus, so I can draw that dashed line again between the lone pair and the delta plus atom, and that is what represents hydrogen bonding. Now, fluorine and hydrogen is easy, and you know I don't like to say the word easy in a chemistry class because it's not an easy subject. But in terms of these types of bonds, there's only one possibility for an HF bond, right? There's Avogadro's number of molecules where you can have a hydrogen oxygen or a nitrogen hydrogen bond, but there's only one way to make an HF bond, and that's just a bond between H and F, okay? So it actually simplifies things a little bit. But again, here's another hydrogen bond, right? I like to draw the delta negative by the more electronegative element, draw the delta positive just to show the reader I have opposites attracting, and then I draw that dashed line like that. Give me a thumbs up if you follow me on the concept of hydrogen bonding. If you studied biology again, if you looked at the structures of the tertiary and quaternary structures of proteins, you would have studied hydrogen bonding. Heck, if you studied the secondary structure of proteins, you would have looked at hydrogen bonding. If you studied DNA and the double helix, you would have covered hydrogen bonding to some extent in those kinds of classes, in those types of biology classes. Hydrogen bonding, very important concept. Is anybody with me on hydrogen bonding? I don't see anybody giving me a thumbs up. Does anybody have a particular question that they need to ask? Again, feel free to stop me at any time. I realize this is not the most cinchy thing out there. It really isn't. This section is, in fact, largely conceptual, right? It's just imagining what's going on, right? And then being able to look at a molecule and say, well, there's a dipole here, yeah, so dipole-dipole forces, right? Very much a conceptual chapter. Okay, good. Thanks, Grayson. I'm glad you're following me along here. Here's just some figures that I took straight out of our textbook. Okay, I thought they were good, so I included them in the slides. Here's an example of a cation and an anion. Sorry, these are both cations, aren't they? Shoot. Anyhow, so we have a sodium cation and a magnesium cation. And I explained to you earlier on in the class why a magnesium cation would be smaller than a sodium cation, right? You've got two lost electrons, so the effective nuclear charge is going to be greater for Mg2+, so its radius is going to be smaller. But that's neither here nor there. But you can see that the interaction between the sodium cation and the delta minus, and these are the delta pluses, right? This is just trying to show you H2O is what it's showing here, okay? And they're showing you the delta pluses and the delta minus, okay? But they're just showing it in a space filling model. Anyhow, but you see that the interaction is weaker than the interaction between the magnesium and the oxygen. Why? Because it's based off of Coulomb's law, which is the force is going to be proportional to the charge. Sorry, the product of the charges, and here you have a 2+ charge, here you have a 1+ charge. So the product of the charges divided by the internuclear distance, or the, yeah. And so since this is also smaller and has a double charge, it's going to be a stronger interaction. What I meant to say is that this diagram over here is actually showing an anion in solution. This is an anion, and if you're wondering, Mr. Dion, how do you know that that's an shoot, it's not an anion, is it? That's a cation. Sorry. If you're wondering, Mr. Dion, how do you know that that's a cation in solution? It's because all the delta minuses on all the water molecules are pointing towards it, right? And they're all attracted to that. And that's what we call solvation. Okay, the cation is being solvated. If you're wondering, well, what if you had an anion in there? Said anion, what would happen then? Well, in the case of an anion, the water molecules would all line up the opposite way. You'd have them looking like this, okay, where the hydrogens would be in the back, okay, and that big old delta negative from the oxygen would be, sorry, I think my Moderna vaccine is having a bigger effect on me than I thought it did. Anyhow, so the delta pluses from the water are going to be aligned with the negative charge. So we have our delta plus like that, okay, and then our delta minus will be pointing away like that. Anyhow, there you go. But that's just an interaction between a permanent dipole and an ion. So these are ion, these are both ion dipole forces. All right, the next figure is okay. If you just look at it at face value, it doesn't give you a lot of information. But the concept here is just showing you if you have polar molecules, so molecules that have a dipole already in them, you can imagine that this is maybe a liquid sample. If you have a bunch of acetone molecules, what are they going to do? They always seem to line up so that you have, an interaction between positives and negatives, right? They're going to be attracted to one another, and that is going to, maximize the strength of the intermolecular forces. So that's the whole idea here. Nothing really more than that. So we can move on from there. So with that, all those thoughts in mind, and we covered dipole-dipole forces, we covered hydrogen bonding, and we also covered London forces. What types of intermolecular forces exist between the following pairs? Well, before we answer this question, I just want to mention what's called a van der Waals force. If any of you have taken a chemistry class anywhere else before, or if you read the book carefully, you might have saw something called the van der Waals force. When you have a dipole-dipole force, so dipole-dipole force, or if you have a dipole and an induced dipole force, or if you have a dispersion force, okay, these collectively make up what are called van der Waals forces. Personally, I mean, every chemistry textbook says van der Waals forces in it somewhere. Personally, I'm not a big van der Waals forces guy because I like to, describe them in terms of really what they are. Like I like to say, well, I've got a dipole-dipole force. I've got a London dispersion force, right? A dispersion force, again, is the same thing as a London force. And then if I have a dipole-induced dipole, I like to call it that. Now, one more we have on top of that is the hydrogen bond, okay? We'll just say H bonding, which is not a type of van der Waals force. All right, with all that in mind, could anybody take a stab at what kind of intermolecular forces we would have between HBr and H2S, hydrogen sulfide and hydrogen bromide? Not an easy question, maybe, but could anybody just take a stab at it? Yeah, just a guess? Yeah, I definitely think that there would be a dipole-dipole force. So somebody said maybe a hydrogen bond, and there's definitely hydrogen atoms in here, but since there is no oxygen, nitrogen, or fluorine, right, there's no capability for hydrogen bonding. You've got to have hydrogen and oxygen, nitrogen, or fluorine present in order for hydrogen bonding to be a thing. All right, if we look at the Lewis structures of HBr, there's a dipole going this way, And if we look at the Lewis structure of H2S, there's a dipole, an overall dipole going that way. So I'll erase these. So these are both are polar molecules. So we'll put both are polar. Therefore, they're going to experience dipole-dipole forces, dipole-dipole forces, and they're also going to experience London forces or dispersion forces. In fact, every molecule is going to experience London forces. So you can always include London forces. And again, if you want to call it a dispersion force, there's nothing wrong with that. And so that's the answer. Dipole-dipole forces and dispersion forces. What about the next one? I've got Cl2 and Br2. Does anybody have an idea about Cl2, chlorine, and CBr4, carbon tetrabromide? Anybody get an idea about these ones? Let me ask you this. Are either of these molecules polar? Yeah, thanks, Christina. Absolutely. Hey, my students are on the ball because I don't think this is an easy question. You guys are crushing it, right? Chlorine, here's the Lewis structure of chlorine. Chlorine is non-polar, no dipole. And if I draw the Lewis structure of CBr4, carbon tetrabromide, I'm not going to draw in all the lone pairs, but you see that all the dipoles cancel here. So this is also non-polar. If I have two non-polar molecules, what's the only possible interaction they could have? Would be dispersion forces. We'll put here dispersion only. Right? And dispersion is based on polarizability. Oh, I didn't give myself a lot of room here. I'll just go over the next one with you. In nitrate, you have an ion, right? So we have an ion. And then iodine is nonpolar, right? Because I2 is a totally nonpolar molecule. And so here we would have ion-induced dipole, right? So maybe for C, why don't I use a different color? For C, I would have ion, right? Because this is an ion. And then from the iodine, which is nonpolar, I'd have the ion-induced dipole force. And let's go over the last one quickly. You have ammonia. Here we go. Ammonia has hydrogen bonding. If you draw the Lewis structure of ammonia, right, you've got the nitrogen-hydrogen bond, and so you have H bonding. So this one, H bonding means that the molecule has a permanent dipole. So we have a dipole over here. And C6H6, that's benzene. That's this molecule here, 1, 2, 3, 4, 5, 6. We alternate double and single bonds, and we put a hydrogen on each one of these. Benzene is totally nonpolar, no dipole in the molecule. And so we're going to have dipole slash induced dipole forces. And again, all have dispersion forces. Dispersion forces are present in every molecule to some extent. Okay, there we go. Let's get back to that hydrogen bond for a second. This is a hydrogen bond being represented in an electrostatic potential map between, this is called formic acid. Formic acid. Formic acid is a Lewis structure that looks like this. Something like this. There we go. So that's formic acid. That's this molecule over here. You can see that the double bond to the oxygen must be over here because we have a big old delta minus over here. And then it's being attracted to water. Well, again, like I told you before, if you have a water molecule like this, the hydrogen is going to be delta plus. So this is your delta plus right here, and there's going to be some kind of force of attraction there, but it's going to be a very strong dipole. Again, I repeat, in order for you to have hydrogen bonding, you've got to have a hydrogen bond to at least nitrogen, oxygen, or fluorine. Now, I told you about polarizability, and I said, and I'll back up and show you to prove it. I don't want to misspeak here. I said, when we talked about polarizability, I said that as the number of electrons increases, or the more diffuse the electron cloud increases, the intermolecular forces are going to get stronger. So that means it's another way of saying that if you have more electrons, right, as the molar mass increases, that dispersion forces should increase as well. So normally, if we go down a group and we compare similar compounds going down a group, as the elements get heavier and heavier and heavier, the intermolecular forces get stronger and stronger and stronger. If you look at all the hydrogen compounds of group 4, okay, so these are group 4A hydrogen containing compounds, right? What are the elements in group 4? Look at your periodic table. You've got carbon, silicon, germanium, tin, and then after that you have lead. It's not on here. But look, if you go from CH4 to SiH4 to GeH4 to SNH4, what happens to the boiling point? It gets higher and higher and higher and higher and higher. Why? Because the electron cloud is getting bigger and bigger and bigger, and the dispersion forces get increased. Now, if you look at the trend for groups 6, 7, and 5A, you see that it's a very different trend, isn't it? Right? Once you get past the second period, where you have water, ammonia, or HF, that the boiling points drop. Not only do they drop drastically, but they all increase, right, with the increasing molar mass. But again, this question just kind of, or this slide rather, begs the question, why do water, HF, and ammonia have such high boiling points? And again, it's because they can hydrogen bond. Now, again, a very astute question would be, well, why, Mr. Dion, is the oxygen hydrogen bond so much more special than the sulfur hydrogen bond? All right, I've got HO versus HS, let's say. Okay, it's based on a couple of things. It's based on the fact that oxygen is more electronegative than sulfur. It's also based on the fact that it's smaller, right? We know that Coulomb's law says the force of attraction between the two charged species, or partially charged, is going to be equal to the product of their charges divided by the distance between them. So we got a double whammy here, right? The F is going to be really big if not only this has more delta negative on it, but it's also smaller. So that means that Q2, let's say, is getting bigger. Sorry, that was supposed to be a Q, not an O. It's getting bigger, but also the radius is getting smaller. And both of those are going to cause the force of attraction to go up. Okay. And again, it only occurs for these three molecules, or these, three types of bonds: the oxygen hydrogen bond, the fluorine hydrogen bond, and the nitrogen hydrogen bond. Now, there's another couple of outliers here. You might be wondering, well, why aren't they in order? Fluorine is more electronegative than oxygen. Shouldn't it have a higher boiling point, HF, than the boiling point of water? Well, the reason why the boiling point of HF is lower than that of water is, look, if you have two molecules of HF, there's only one possibility, right? You've got the delta plus on the hydrogen, you've got the delta minus on the fluorine. So one of the lone pairs on the fluorine is going to interact with the delta plus like that. Now you've got two lone pairs left over. What makes water so special is that in a water molecule, not only do you have two delta plus hydrogens, okay, but you've also got two lone pairs, both of which are delta minus. So hydrogen bonding is basically maximized in water. That's one of the reasons why water is such a special compound. All right, let's answer this question. Which of the following can form hydrogen bonds with water? We've got some interesting compounds here. I'll tell you what they are. This one's dimethyl ether. It's used as a propellant in aerosol cans, like something like maybe whipped cream or canned, spray paint or something. Here's methane. It's one of the major components of natural gas. Fluorine is a dangerous molecule. Don't want to think about that. It can cause explosions. This one here is formic acid. And of course, you know what a sodium cation. All right. Could anybody tell me, if I label these, if I just label them A, B, C, D, and E, could anybody tell me which one of these would form hydrogen bonds with water? Yeah, the answers are, the only ones would be A and D. Those are the only ones that would form hydrogen bonds. Let me explain. If I draw A, which is the dimethyl ether molecule, I draw the bent geometry around it like this. Those lone pairs are delta minus. So if a hydrogen molecule, or sorry, a water molecule is close, then the delta plus can be attracted to that delta minus like this. This one here is formic acid. I'll draw that out quickly. Formic acid looks something like this. You get another oxygen like this, okay? Well, here we have a delta minus on this oxygen. We have another one over here. Well, let's say there's another water molecule near that. I have a delta plus over here, and so there's going to be an attraction between the delta minus and the delta plus. Methane, in order for hydrogen bonding to occur with water, you've got to either have a nitrogen, oxygen, or fluorine that is got a lone pair that's polar enough that can participate in hydrogen bonding, or you've got to have a hydrogen with a delta plus on it. So yes, there are hydrogen atoms in CH4, right? But this CH4 is a nonpolar molecule, right? Nonpolar, and so there are no delta pluses and no delta minuses in CH4. The same thing occurs in the F2 molecule. Yeah, you've got two fluorines, you've got lone pairs, but there's no dipole in the molecule. So the fluorine isn't going to be delta minus, and so that's not going to form a hydrogen bond. And then a sodium is a cation, so that's not going to form a hydrogen bond as well.